Hello and welcome to the CIBSE West Midlands Region CPD webinar on pre-insulated heat network design and specification. Just a few housekeeping tasks before we get started. Please use the chat function to ask any questions during the presentation. A copy of the presentation slides should be available after the event, hopefully. CPD certificates will be sent out automatically afterwards once I've checked you in via your registered contact details. I'd like to take the opportunity to thank you for joining us for today's session, but also thank Vikram for sharing with us what he's going to today. I'm really looking forward to it. Pre-insulated heat network design and specification. So today's session is an introduction to CPV and who they are and what they do, including CPD, innovation in heat networks, chemical, hazardous drainage and critical infrastructure piping solutions. Unfortunately, both Andrew Sims and Chris Sykes aren't able to join us today, but Vikram has valiantly stepped into the breach, so thank you very much for that. Andrew Sims of CPV has 20 plus years of installing and managing some of the largest heat networks in the UK. Chris Sykes has 20 plus years of piping solutions for the industry. And our speaker today, Vikram, has 12 years and more in experience in the industry, mainly in product and project management. Vikram, great to have you here today. Thank you very much and looking forward to what you have to say.
Thanks a lot for having me. And I do see that Andy Sims has joined. Just going to check with, oh, he's dropped out again. His signal is really weak. So I will be presenting today on CPV's behalf and on behalf of Mark and Andy. So I'm just going to bring up my presentation and just going to, I take you can all see this now. Josh, could you confirm?
It's not coming through yet. Have you shared your screen?
Through. Yeah, bear with me. I think it's my screen, which is issue here. There you go. That should come up.
It has, but if you go into presenter mode, that's brilliant. Lovely. Thank you very much.
Okay, let's get this started. So we're going to look, as Josh said, we're going to look into the heat networks and the various options and the materials which are available on the market. There's also going to be some insight into how installations take place and the cost savings and everything else that goes into these heat networks. To start off, I'm going to give you a brief overview of CPV. CPV have been in the market since 1948, predominantly extruding polymer pipes back in the 50s, and for various applications such as drainage and pressure systems for commercial and for domestic applications. That spiraled on to pre-insulated market in the early 80s, where heat networks started, and that's moved on even further into the early 2000s, where polymer systems have been predominantly the focus, along with traditional steel systems. The PEX and the other GRE material, which is also come into the fray with all the new district heating networks, we're going to have a look at that as well. And CPV have been a major player in that in the past 10 to 15 years. There's also a lot of focus on offsite fabrication, which predominantly is looked into at data centers and other applications, but also is a massive impact or cost saving on district heating schemes. So without pulling any further, I'm going to go into the heat networks and everything else. And as Josh said, any question and answers can be either put in the chat or I can answer it at the end of the presentation. So as stated before, chemical and drainage applications is what was the main focus for CPV, or was the market in the 50s, but that's moved on to critical infrastructure solutions and bespoke applications for various applications in the commercial and domestic industry. And the focus on this CPD is predominantly on district heating concepts, distributions, and the design aspect, as well as the installation considerations. So a district heating network, a lot of people who are on the CPD probably have knowledge or have experience in this, but I'm just going to reiterate what's actually constitutes of these networks. So you primarily have the center energy center where the water is heated and distributed to feed either buildings, or it goes into a plate heat exchanger, which you would see. I'm going to jog back a few slides and go back again. So the central heat source where it's distributed and goes into either a secondary network or a heat distribution substation, where it can be either reheated and distributed, or it goes directly into your commercial buildings. The reason for these heat networks is predominantly bringing down your net. We are all focused on the net zero carbon. So that's the focus. And there's a lot of waste heat recovery systems which are generated and can be used to heat the energy center. So there could also be, or there are other alternatives, such as alternative fuels, and there are higher efficiencies using these larger heat networks. The catalyst of this entire growth is obviously driven by regeneration, and with a zero maintenance for a 50-year life cycle, predominantly is the focus for these large-scale district heating networks. So what does it actually involve, and how is the water actually distributed in the network? So your primary focus is on your service pipe, your insulation, and the outer casing, where water is distributed through the service pipe, and the insulation acts as to reduce the heat, and the outer casing protects the insulation as well as the service pipe. We'll look at it further, and or what are the other options in the market, the various insulations, the service pipe, and the outer casings in the slides to follow. To start off, major considerations need to be based on to select a system, that is what service pipe you would select and what would actually be involved or would suit your requirement would be dependent on your flow and temperatures and the pressures, your characteristics, your thermal stresses, and thereon spiraling onto the size range and the installation jointing, the maintenance and everything else to go with that to make it a more sustainable system. Traditional systems generally have always been on the higher side of operating temperatures and pressures, and that is predominantly coming down with the need or a lesser need to run at those temperatures and pressures. So before you start or you consider going through and designing a system, the service pipe needs to be looked at, as well as all your necessary certifications for any materials that is a certified product to be used in the district heating market. The traditional steel systems have always been a major player in the past 50 years, and that's what we're going to base it on, and which still has a massive market. And for larger district heating schemes, it's still used very extensively. So as far as steel systems go, so as you can see, the chart shows you the size range it can meet. So a larger system would have a larger diameter of pipe, and the temperatures and pressures that steel systems can hit are really good. So it's always the traditional system has been really good and has worked well, but it does come with a few drawbacks when you consider other materials. So when you're designing a system, these need to be taken into consideration. So selecting your material. So a steel system, although it hits your temperatures and the size ranges, if done properly, and all the considerations such as your thermal stresses, your joints, and the ease of installation and the size range is looked at properly, and the flow characteristics, you would have a really good system. But then the maintenance is also a lot, or it could be a lesser, depending on how the system is installed. But steel is also prone to corrosion, so that needs to be factored into. And when you compare it to polymer systems, you will see the difference. So flexible, there are many polymer systems. Flexible and the polybutylene, to start off with, were used and proven to be used in sanitary and plumbing applications for underflow heating, and that spiraled on for it to be used in district heating schemes, although operating under lesser temperature and pressure. So those will be on the smaller schemes, and there are a lot of advantages, and obviously that may not a disadvantage, but obviously it cannot run at higher temperature and pressure. So those are the constraints. So that needs to be considered for larger schemes. The size range which it can meet is a constraint, because there will be sizes only up to 6-inch or 160 mil, which polyprop or the PEX system can meet, and the polybutylene as well. And the size range obviously has an impact on how big the scheme is. And the advantage with that, though, would be your thermal stresses, which is far lesser compared to a steel system where the forces are greater. You have a maintenance-free system. The corrosion, that's maintenance-free if the installation is done properly. Corrosion issue is not seen in plastic system or the flexible polymer systems. The flow characteristics are very good because the inner surface is very smooth. That's moving on to our polyprop systems, which are rigid systems, which they fall under, which help with the ease of installation as well as the size range. But again, with polymers, you have a certain temperature which you need to work to, or maximum temperature, which is not the same as steel systems. And the rigid polymer systems, opposed to steel, where you can see here, there's an overlay there, which hits all the marks, such for your jointing, your temperature, pressure, the risk of corrosion, flow characteristics, maintenance, ease of installation, size range. The rigid systems of polymers can meet all that. And that's a typical example of a pipe in a trench with electrofusion jointing, which we're going to look at different jointing methods as well, which needs to be considered when you are working with different materials. And the image there is a twin and a single system, which is transferable to traditional steel systems, as well as adopted in rigid polymer systems, as well as flexible polymer systems. GRE, we're going to touch a little on that because a product which is predominantly used in the petrochemical industry is also a good material or a good selection for these district heating schemes, because they can meet the temperatures and pressures which are greater than polymer systems, as well as, though it falls a little under the steel, it predominantly hits most of the design aspects of steel, and that is a good material to use, given, or to select, given the money you're going to spend, or if the scheme needs it. So a GRE is very similar. Again, we are overlaying it over a steel system, and as you can see, it hits the right marks even better than rigid polymer systems, because it can hit higher temperatures and pressures, and the same aspects of maintenance, which is far lesser, no corrosion, and the flow characteristics make it a very viable system for larger district heating schemes, as well as small ones. The jointing of GRE is a little different than to rigid polymer systems and steels systems. As you can see, there's a cross section of a joint where it's an adhesive joint which is upon a glue system, as well as there's a heating blanket which helps the glue to set. Going into polymer systems, there are also options of reinforced polymer systems, which you can see here hit the higher maximum temperatures. So the flexible polymer system, which can run at a maximum operating of 80 degrees, is exceeded on these reinforced systems, where 115-degree maximum peaks and continuous at 95 kind of set the bar for flexible systems, or make your material selections or the options of selecting these materials also good, which run up to again 6-inch on flexible systems is what you would see the max. And overlaying it against steel, it's far better than traditional flexible system, which has the PEX primary material. This is reinforced, hence it does the size range and it meets all the criteria of the maintenance risk of corrosion characteristic, flow characteristics, and the thermal considerations. The jointing is a pressed fitting. We're going to look at the fittings as well as a separate slide here. But as you can see, these systems, the change in directions or the way it's laid in a trench makes it a far easier system to install on site, or if a trench with a lot of services in them, these flexible systems work really well. Your joints. Okay. So as you can see, traditional systems are, the steel system is arc and gas welded. We've also touched base on the socket adhesive system of the GRE. The polymer systems, the butt and the electrofusion are widely used above and below ground. And it is a proven jointing technology, as well as the mechanical press fit fittings used with reinforced polymer systems. There are also mechanically bolted systems, which are seldom used, but can also be used below ground. But what you would see traditionally on rigid systems, that is polymer, would be butt and electrofusion along with your gas welding on steel. And the outer joint, there's a slide which is on your right, as you can see. This is a new system where the electrofusion coupler is half welded or pre-welded and prepped prior to going to site, which makes the ease of installation on site far easier, where the need for clamps, peeling of the pipe is all taken out. And the outer joint, or the void where these joints are filled with, is going to be looked on the next slide, which I'm going to, okay. So let's go back here just to give you an insight. So the foam shells which you see, there are various versions of them. You could either have a two-part liquid foam which is poured to fill the void within the outer casing and the service pipe to make it a fully sealed system, and various options of jointing for the outer are also available, such as electrofusion jointing, which are a wraparound or a slide-on sleeve, or a heat shrink joint, which is used extensively in traditional systems as well as the current systems. So a graph of or table where you can see the different jointing methodology of the various systems. This slide obviously will be shared after the CPD, and there's a lot of literature available on our website to gain knowledge into the different jointing technology as well, what each system comes with. So moving on design considerations for these systems. Bonded and non-bonded, there's a clear difference between them because that has a massive impact on your heat loss, which we'll again look at in a later slide. But a bonded system and a non-bonded system basically have, as you can see, the bonded system creates a bond between the service pipe and the insulation, thereby minimizing the heat loss, whereas a non-bonded system is a wraparound foam, which on the downside would have an issue, possible issue with expansion, where on a bonded system, where the service pipe, the foam, and the outer casing moves in unison, opposed to a non-bonded system. And the lambda value that is here, which has an impact on your heat losses, is critical to a non-bonded and a bonded system. So as you can see, the lambda value is far greater on a non-bonded system, which making it either having multiple layers of this insulation to meet the requirement, making the trench bigger, as well as your cost going up. A bonded system has a massive benefit of no water ingress should outer joint not be properly installed and a leak happens. Typical graph showing the heat loss between a bonded and a non-bonded system, a visible indication that why a bonded system needs to be used or selected. So there are different insulation thicknesses which have an impact on your selection or at the design stage, where obviously the cost is a massive factor, but over a period of time, having a greater insulation would have a greater benefit. A Series 1 is a traditional system where you have a minimum insulation between the outer casing and the service pipe, and that can be enhanced on the Series 2 and 3. A greater insulation gives a greater or a lesser heat loss, making the system more cost effective over a period of time and significantly decreasing the cost overall to the end user. Aging from foam. Okay, and so that is something which has an impact, obviously, on the system itself. Foam which ages, obviously, it decreases the performance, as well as there are multiple barriers which can be used in order to lessen or decrease the aging of the foam, which is also need to be considered, either having a thicker outer casing should a leak happen, or a barrier within the casing to basically decrease or prevent any leaks or gases escaping the system. What traditional systems have predominantly had because of the issue with corrosion and leaks of the service pipe weld or any leaks in the system, a copper and tin wire or a surveillance system is a compulsory on steel systems, that is the traditional steel systems, which is not seen in polymer systems because the issue of corrosion or leaks are far lesser. But the leak detection system can also be incorporated or implemented in the system should a need arise. And these systems can either be used with leak detection systems or with a leak detection and a trace heating or a maintained trace heating system should a need arise. All it does is you could pinpoint the leak, or it could detect a leak, which is similar to any surveillance system, which is used on the steel, which can also do the same on the plastic system. This leak can be pinpointed to a close range of about 1 meter within the leak. We are not going to be looking into surveillance systems, but just to give you an insight, what you need to consider should you be using a rigid polymer system or a flexible polymer system opposed to a traditional system where a surveillance system is a must. The outer casing. The outer casing of buried systems have always been either low density polyethylene or high density polyethylene. The HDPE is used in traditional seal systems as well as polymer systems, and the LDPE used in flexible systems. And there are also alternative materials in the market where you can use aluminium as the outer casing, steel casing, or a barrier with for contaminated ground, or a thicker casing, spirally wound galvanized steel for above ground as well, and touching base on high modulus polymer systems, which is the next generation, which also have a massive advantage on alternative materials which can be used. The outer joint, which we spoke about a little earlier, the traditional systems would have been the heat shrinkable double seal joint, where it's a joint which is slid on prior to the service pipe connection being done, and then is slid back on and shrunk down, and either a two-part foam liquid or a half shell is used. The heat shrink joint has a mastic which creates the bond between the service pipe and the inner of the outer joint. But you also have the clip-on systems where it can be retrofitted, where you would slide in a rubber ring prior to doing the service pipe connection, and a clip joint, that is the mechanical shown in the image, is a two-part clip which clicks together and foam is poured into the void. As you can see, it is far bulky, making the trench possibly a little bigger. So another design consideration. Fusion joints are far more robust and are used extensively for below ground systems, as well as for contaminated ground. It's a good consideration to use these. There are slide-on electrofusion joints. There are also the wrap around, which can be retrofitted, which helps with the process of when commissioning a system. These can be retrofitted, which is a massive advantage. So operating temperature and pressures. This is something which dictates your design considerations. For larger heat networks, it's still steel running at higher temperatures, but as you can see, the GRE and the reinforced polymers sit right in between them, which are more so being used or being considered by designers for systems which are running at temperatures between 110 and 120 degrees. And smaller schemes, the PEX and the PB are used. And going on to that, into our next slide, which is the pressure considerations. Obviously, steel has can run up to 50 bar, and all other systems are running at a maximum of anything ranging between 6 and 15 to 16 bar. So if you're looking at high pressure systems, steel is your go-to material. But this can also have your issue with the surface roughness, where you need to consider your corrosion or your surface roughness between polymers and steel, where there's a massive advantage of using these polymer systems, where your flow rates and your flow characteristics will be maintained through the life cycle of the job or the project, rather than steel having a 37.5 decrease or increase in surface roughness. Stress analysis, a major consideration for traditional systems which have always impacted large schemes, where the cost is driven up due to having expansion bellows, change in directions, or any other compensators to be used. to compensate for any thermal stresses where traditional systems tend to have an impact. So there are packages in the market where SysCMA, which is used, which is a computer-aided design, which spits out a report with what change in directions or what considerations need to be done on schemes. Cushions are generally used around these loops, as you can see on your right-hand image, to make sure where the change in direction is, the expansion is absorbed. This is not obviously relevant to polymer systems, which take out that massive cost, as well as the need for any expansion considerations for polymer systems. Moving on to hybrid systems, which is seen more frequently in the last 5 to 10 years, where steel and polymer systems are used in tandem. So for large schemes, this is a way out where you can use steel for your ring mains from the energy center, and polymer systems, depending on your temperatures and pressures feeding the different substations or your buildings, can be used, which when overlaid, your wholesome experience of using a hybrid system would be your answer, depending on what you want to achieve or what the client's requirement is. A hybrid system gives a lesser maintenance, better flow characteristics, as well as the risk of corrosion and your thermal stresses have been looked at or reduced largely using hybrid systems, especially on the spines or the branches coming off going into your buildings by using polymer or GRE material. And as you can see there, the rigid polymer systems have a great effect on hybrid solutions. And your GRE has a good impact on it, as well as your hybrid systems, as you can see, gives you the overall requirement for a client or your network. So the hybrid solution is what most people would be tending to lean to in the future. So what it does is it saves time. It obviously improves your quality, the risk of or reduces your waste and lowers the cost considerably. Off-site fabrication. This is something which is being used more common, where the need for reduction of site time and ease of installation has pushed the industry towards these off-site fabrication, which the main materials are installed and when required to help with either during the project or before the project, if design considerations or everything else is taken into consideration, off-site fabrication reduces the risk of or reduces your cost massively. And this can be achieved by bin modeling, which is used by designers as well as a client requirement on most large scale projects. And if you have any unforeseen requirements on site, off-site fabrication would be a go-to, because a lot of time the requirement of a joint cannot be met on site, and retrofitting or pre-insulating a system where it's done off-site and then dropped into, as long as your coordinates are met and the BIM modeling is done correctly, saves a lot of time and is a hassle on site. a offsite fabrication of a plant room for a data center, which was done. As you can see, the need for the number of joints is greatly reduced on that steel spool, which is right in the middle. So that is saved at least 6 welds and 6 outer joints by doing the offsite fabrication. And that is a possible design consideration should all the necessary data be available at the time and a fully coordinated model is achievable. So we're all driving towards net zero carbon, and hence the 4th and the 5th generation polymer system is what everyone or the focus is or needs to be, reducing the temperatures and pressures and the need for having largest systems using polymer. So that brings on to our drive, where the drive for net zero carbon would have your hybrid system, which is more sustainable, which has higher environmental credentials. It's high performance, lesser risk, and ease of installation on site, overall reducing the cost. Certain standards which you need to be aware of during specifying materials are your design and installation EN 1349 and 13941 and the EN 253 for district heating. The code of practice, which is the standard, the CIBSE one, which for heat networks is which is a clear measurable output for effective network. I'm sure most people already have access to this. This can also be either sourced from the website, and this needs to be considered during design and needs to be used when you are designing a system as well as any network. There should always be obviously adequate supervision, experienced installers, training, which is needed for inner and outer jointing, your stress analysis, and your testing of the system as well, whatever is needed, depending on your traditional systems where NDT is required or your standard system where a hydraulic pressure test is required. That all needs to be considered during installation as well as specified in the documents. And as we're moving towards the BIM, so a good documentation process and meeting BIM requirements is a need for installers. So where we stand now is we're looking at corrosion-free.
It's just a note from one of the attendees just noting that the CP1's been updated slightly.
Okay, fine, no problem at all. Thank you for bringing that up. So that is CP. Does it go to CP2 or? So yeah, it's just the version of it. Is it 2000?
Yeah, 202, but it might be 2022 or 2023 version, I think.
Okay. Made a note on that. We need to update that. So all what people or we should all be aiming at is 25-year design life with a corrosion-free system, where the solution would be a hybrid for large schemes, where GRE with stainless steel or FiberFlex Pro, or depending on your temperature and pressure, which is resulting in a corrosion-free upgrade utilizing the pros and cons of the materials which have been discussed in this CPD. So a few case studies, which I'm going to go into for district heating network. So that's a DI. I can't actually tell you the project itself, but I've just mentioned the DIO site there, and a few others where polymer systems have been used on what sizes and there's always need to improve and innovate, so that we're at a point where hybrid systems are the next go-to or already being looked at. So it's something which designers need to be aware and consider when you design networks. So the traditional systems such as steel and copper, which are still a massive player in the market, and the different polymer systems which are on offer, and the flexible systems as well with the offsite, which the offsite fits in with traditional steel systems as well as the polymer systems, which will aid to a very cost-effective and good hybrid system. So that is where we stand, and I would thank you for your time which you've given, and if you have any questions, you can fire it now,